recording. Hello everyone, hello Morbaji _M, Jonja, Joy, Marionette, Mika, Nida, Ricky, Shadow, Shaza, TD, Jesus, Caris, Tony, Yaninte, Atino, Leila, and who's just joined? Sid. Hello Sid. Okay, so today we have these three LeetCode, and we finished week 5, so this is the last 3 we have this week. If you did miss this one, you can find them in the recording 17, 18 and 19. And the next week we have this one, so we're gonna keep going like we plan. So let's start from the today one, these 3. So we can start from the first one. I think it doesn't matter that much. So let's read this one and see what's the problem we are having here. And please, as always, feel free to open mic, talk, discuss. You have question, write in chat if you can talk. Don't be scared. Okay, let me share the link. Don't be scared, and you may feel like imposter syndrome that you maybe don't know. That's a lot. Trust me, we don't know anything here. We are just learning, like you, like me, and that's all. Like, we're here to learn from each other. So let's start. Lowest common ancestor of a binary search tree. Given a binary search tree, BST, find the lowest common ancestor LCA node of 2 given node in the binary search tree. According to the definition on Wikipedia, the lowest common ancestor is defined between 2 nodes, P and Q, as the lowest node in the tree that has both P and Q as descendant, where we allow the node to be descendant of itself. Okay, this can be confusing to understand, but we're gonna get there. So the lowest common ancestor is defined between 2 nodes, P and Q. Okay, let's say 9 and 8, as the lowest node in T that has both P and Q as the descendant, where we allow a node to be descendant of itself. Let's see this example. Maybe it's gonna be more clear what they are talking about. Example 1, we have 6, 2, okay, and because it's a binary tree, notice that the left is less than the root and the right is greater than the root. So 7 is greater than 6, 9 is greater than 6. Tafi, your mic is open. Please, if you can mute. Tafi, can you hear me? Tafi, hello. Okay, temporarily. What is the image? Okay. Pop, 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 pop. Okay, we continue. So we notice here that 8 is bigger than 6, 7 is bigger than 6, 9 is bigger than 6. So always the right side is bigger than the parent. And 2 is less, 0 is less, 4 is less. So this is a binary tree. And the P here is gonna be 2. Let me choose 2 is P, and Q is 8. Now what is the LCA of this 2 and Q? Lower common ancestor. They say it is 6. How did they do that? LCA of node 2, 8 is 6. Okay, because the lowest common node that they split on is 6. Let's see another example so it can make it more clear. Let's see this one. This one they said 2 and 4. and the low LCA is 2 itself. The LCA of node 2 and 4 is 2, since a node can be descendant of itself according to the LCA definition. Okay, this is gonna be confusing a bit. Let's take it to our lab and try to understand it more. Okay, so how we know that two of these nodes are LCA, which means like lowest common ancestor. Given a binary tree, find the lowest common ancestor node of two given nodes. So they're gonna give us like two nodes, and we need to find the lowest common ancestor. So if they give us 2 and 8, the lowest common ancestor is 6, right? Here with the split. If they give us 7 and 9, 7 and 9, of course this is common between them, right? But this is also common, and because we are looking for the lowest, which means the closest one to them, the most close one, so it's gonna be 8 in this case. So the LCA of 7 and 9 is 8. Now what is one thing that we notice is like this 8 is also ascendant of itself. So we can, if they give us 8 and 9, the LCA is 8, right? Because as the definition say, allow a node to be descendant of itself, and that's what we see out here. Between 2 and 4. 2 and 4, the output was 2, because 2 is descendant of itself and 4 is descendant of 2, so the lowest common ancestor of 2 and 4 is 2. Now how we can understand this with like a simple logic, I don't know. But something I try to make it easy for me to understand is like whenever a node splits, whenever it's split, that a parent node is the lowest ancestor of the both, right? What we can say here, just if someone have questions, still didn't understand what lower ancestor mean, or like lower common ancestor mean. Let's give an example. What is the lower common ancestor of 5 and what? Let's say easy one, 3. What's gonna be? Anyone? 4. Okay, 4. Now can we say 5 and 7? What are the lowest common ancestor of this? 6. Yes, 6, because this is the one. This is where they split, I think. Let's see. So to reach 7, we need to go 6, 8, 7. 6, 8, 2, 7. To reach 5, we need to go 6, 2, 4, 5. So the only one that are common is 6. Yes, special character, please go ahead.
Okay, it's about the lowest common ancestor of 3 and 5. Why is it 4? Because for me, I see that 2 is the lowest, but why we choose 4 as the lowest common ancestor? Is it also supposed to be the lowest and the closest at the same time?
So the lowest is mean the level, the lowest level. So if we say 5 and 3, if we go back to between these two, 3 and 5. So to reach 5, we're gonna go through 6. We're gonna go through 6, 2, 4, 5. To reach 3, we're gonna go from the root 6, 2, 4, 3, right? So they have this common, this common, this common, but the lowest is the level close to them. So this one, right? So this is the lowest common ancestor, which is 4.
So it just means that it's the
Yeah, the most close one to them.
Because with that explanation, I can say that it will always be the one just in top of them.
Can you repeat last part?
Okay, with what you explained, I think it's always going to be the one that is on top of Bob.
Yeah.
So,
yeah. Okay.
Thank you.
Who is like still trying to understand? It's okay, we can repeat. Yes, please go ahead.
Okay, like from what I can understand here is like for the lowest common, is it in terms of the value that it holds? For example, we have 3 and 5 now, and then that the lowest common ancestor is 4. Now, what if like what if we have something like 3 and 7?
7 here?
Or yeah, 3 and yeah.
Or you mean 7
5,
here? 3 and 7.
Yeah, 3 and 7.
Yeah.
So now so it simply means that our lowest common ancestor is 6, right?
Yeah, 6.
That is the lowest one that they have. So I think the major point is like we are looking for the two nodes that have the same ancestor. I guess so.
Wait, can you repeat last part?
Like I'm saying, like in essence, what they're trying to tell us is like we should look for a node that is the ancestor of two nodes, the lowest ancestor of two nodes. Yeah. Okay. That's just so. Thank you.
Okay, anyone have any question? Notice that when it is 3 and 7, immediately we say 6. We didn't have to go through this, right? But if there is two number on, so in binary tree, there is this right side and there's this left side. Because we are in binary tree, always this side is negative, this side is positive. What they mean by that? It means like this side is always greater than the root, and this side is lower than the root, right? So 2 lower, 0 compared to 6, 4 is lower than 6, 3 is lower than 6, 5 is lower than 6. But when you go to other side, 8 is greater than 6, 7 is greater than 6. What about 5 and 4? Okay, let's see. 5 and 4. 5 right here and 4. What is the lowest common ancestor between these two? Anyone can answer?
I think it's 2.
2. Okay, let's see. I see someone in chat said wrong answer, and I see someone said correct answer. 6. Okay, who said 2 can explain why 2? Who can explain why 2 and who can explain why 4? So we go to 4 like this, we reach 5, right?
I think it's 4 because they said is the node can be ancestor from itself. So the first one, the first common between 4 and 5 is 4. They have example like this in between 4 and 2. They said 4 and 2, and the first common is 2.
This one right here, they give us 2, and 4, 2 and 4, and the lowest common ancestor is 2, because let's read this definition. The lowest, let's say LCA, so I don't say it all. The LCA of node 2 and 4 is 2, since a node can be descendant of itself according to the LCA definition. So like saying that how, like if we keep the same example 4 and 5, we can say that okay, so they have 6 common, they have 2 common, and they have 4 common, right? Because this is descendant of this, and because 4 can be descendant of itself, it's like we have 4 here, 4, like descendant of 4, so the lowest common ancestor is 4. You know? So the key here is that we know that 4 can be descendant of itself, 5 is descendant of itself, so it's like there is 2 4 here. Just the way to think about it. So is it 2? No. Is it 6? No, the lowest is 4. Who did not understand this one or like have question? I think it's clear, right? I see someone is trying to talk, but you have green circle, but we can't hear you.
Oh, sorry, it's my keypad.
Okay. Yeah. So, like Absamat said, you can maybe ask interviewer to clear that out. But like if he's using definition of Wikipedia, is like it is a node of itself. But it's better to clear that out, right? So it saves you some trouble. Now we understand what is lowest common ancestor. Who doesn't, please raise your hand or like write something in chat. I'll be happy to explain to you. Let's do one more question, see if it is clear for everyone, because I'm also not clear for me. Can we say what is gonna be? Can we say that 2 is lowest is common ancestor of 7 and 9? Can we say that 2 is also common? No, right? I think no, because this is other tree. This is subtree different from this subtree. So the common ancestor is gonna be always in same subtree, right? Okay, let's jump to the pseudocode. Now that we understand it, let's see the question. Given a binary search tree, find the lowest common ancestor ancestor node of 2 given node. So here they give us 2 and 8, we should return 6. Here they give us 2 and 4, we should return 2. How we can code this? Let's see the function they give us. So this is the function. They give us root, okay, the node itself, and they give us P and Q, which in the first example gonna be 2 and 8. Okay, let's write pseudocode. Let's see what we're gonna do. How we need to find first, before pseudocode, we need to find a way to detect ancestor. We know a way because this split. We know that if this value and this value are split, then this one is common ancestor. What do I mean by split? By comparing this value to this. So we're gonna take advantage of knowing this is a binary tree, which mean if they are split, what I mean is they are in a different subtree, right? This is a subtree, this is a subtree. Now if they are split, immediately we know, okay, we found the lowest common ancestor. Now how do we know they're split? Because we know if this is split, that means this value here is always gonna be less than the root, and this value here is gonna be always greater than the root. So if we did like this one, let's do like 7 and 9. Let's do 7 and 9 as our P and Q. So 7, we're gonna check if 7, because we start from the root, right? So we're gonna check 7 is less than 6. So 7 is less than 6. And so we're gonna do and 7. 7. Yeah, 9 is less than 6. Now, if this is condition true, what this mean? If both of these are less than 6, let's see. 7 is less than 6? No, or wrong. And 9 is less than 6, or wrong, because this is 9. So it's not this, which means this both node are on the right side, because if they are both, because if they are like both less, this means they are in the left side, right? So basically we're gonna search only in the right side of node 6. So if this is true, then we're gonna search right side. Wait, true or false? Let me see. 7 less than 6. Okay, I think I lost my thought. Let me repeat. Okay, let's do the other one. So this is 7 less, and then we're gonna have 7 greater than 6, and 7 greater than 6. So we have two conditions. If 7 and 9, if 7 and 9 are less than 6, that means this tree exists on the left side of the node, right? It's gonna exist here. So we can go to the next node and keep looking forward to until we find where is the split. Because if this is false and this is false, what does that mean? That means that one of the node is on the left side and one of the node is the right side, which means we have a split, right? For example, if I choose 3 and 7, if I choose 3 and 7 and they do like this condition, I'm gonna check if 7 less than 6, what is gonna say? It's gonna say false, right? And here I'm gonna do 3 less than 6, true, but because true and false are it's gonna give false, because this is AND, it's gonna give false. So false. We're gonna check again. We said that 7 is greater than 6. This condition is gonna give true. Yes, 7 is greater than 6, and 3 greater than 6, false. Right, this is 3 greater than 6, it's gonna be false. True and false, it's gonna be false. It's gonna be X. That means we're gonna return 6. Return 6. Why? Because the both are in different subtree of 6. So automatically this is the lowest ancestor. Now this is the case when we choose 3 and 7. Let's choose 7 and 9, because we know that 7 and 9, the lowest ancestor is 8, right? So let's see how it's gonna work. Okay, let me clean this. If you are confused, don't worry, it's gonna get clear very soon. Just to do like this example, and hopefully it's gonna be clear. So we said 7 and 9, right? So here we go, 7 and 7 less than 6. is this gonna give true or false? False. 7 is greater than, okay, so 7 is not greater, is not less than 6, false. And is 9, this one, 9, greater than 6? Yes, true. But false and true, it gives us false, so this condition is false. So we're not gonna enter this. But what's that mean? That means this 2 node doesn't exist in the left side, right? Because we know that any node that exists in the left side, that's gonna be always less than the root. So now that we know it doesn't exist in the left side, we can just focus on the right side of this tree. So it's like a recursion, right? So we're gonna enter this right side. Now when we're gonna enter the right side, we're gonna start from where? We're gonna start from the node right, which is 8. We're gonna apply the same rule. Is here it's gonna change from 6 to 8, this 6 to 8 to 8 to 8. So again, 8, 7 is less than 8, true. Is 9 greater than 8? Wait, I have 7, 6. Oh, is 7? Let me write a different color. 7, 10, 8, and 8. Is 7 less than 8? True. Is 9 less than 8? False. So true and false, which mean false. So we're not gonna enter here. That means they are not both exist on the right side. So we're gonna check the other condition. The other condition gonna be 7 and 8. Is 7 greater than 8? False. Is 7 this in here, I think 9. This is 9. Is 9 greater than 8? True. True and false, false. So it's gonna be false, and then we're gonna return what? 8. Because basically this one is in different subtree, this one is different subtree. Okay. It is confusing. Maybe if I write pseudocode, it's gonna be less confusing. Please, if you have question, let me know. Okay, let me write pseudocode. Okay, who did get this idea? Who did understand this? Or who doesn't? The idea of this to check. Okay, that means no one understand. It's okay. Let's do pseudocode and let's see it together. So pseudocode gonna be so we have two of this condition, right? So the condition first one is gonna be if do we call it p, or this one is root, right? So let's call what they give us, p and the ones. Okay, they give us p and q and root. So if okay, let's remind you what was right here. So if 7 in this case, we're gonna say p val, right? Setting val, so the value of this node. If p val less than the root 8, it's gonna be always the root. So root val and q val less than the root 1. If they are in this, if they are p and val are less, that means the these nodes are both exist on the left side, right? So maybe they are here. So I can't return this because maybe this is the lowest common ancestor, right? Or no, it not even maybe, because if they are both in the subtree, that means between these two, there 100% something exists, right? Because if they are directly connected to the root, that means there's a split. That means this and this gonna be greater than the root, and this gonna be less than the root. So there is no way they're gonna be in subtree, in same subtree, right? That's why we're doing this check. So this check, if it is true, we're like, okay, so this both value are in this left subtree. 100%, we are very sure that they are there. And because they are in the left subtree, they're mostly, or they're 100% there's some between nodes. It can be 2 nodes between, it can be 1, we don't know. So we need to travel through this path and see which one, right? So how we gonna do that? To travel is like we're gonna launch like we can do it with the recursion. We call another one on air, or we can do while loop. Let's do while loop. So while root, right? And then we change the root. Root this time gonna become root left. So when we loop again, so while the root, so when we loop again, we're gonna start from the left, which means 2. In this case, if we're looking for 0 and 4, right? But what if it exists in the right side? So it's same code, just gonna change the direction of this, and instead this time we'll go to the left, we're gonna go to the right. Now do we need, yeah, now what if both are wrong? What if this not true and this not true? What that mean? For example, if we have 3 and 7, this 3 and 7, this gonna give us false, this gonna give us false. What that mean? That mean we have split. So we're gonna return the root. Return the root. I'm not sure exactly it was if or else if, but we can do simulation and see if it's gonna work. Okay. Now let's slow down and start from the beginning. So what is lowest ancestor between 7 and 9? When we see in this tree, we immediately say, okay, 6 is common between them. 8 is also common between them, but because we're looking for the lowest, that means the closest one to them, which gonna be 8. Okay, nice. Now, is our code gonna give us 8? Let's see if it's gonna give us 8. So we said while root. So root, we're gonna start from 6. We said if p value, which we're gonna decide this is p and this is q. P and q. Okay, p is 7. I think the order doesn't matter. So p value, which is 7. Okay, 7. If 7 less than the root value, which in this case 6. And let's say this is and q value, which is 9, less than the root value, which is 6. Now we know this is false, right? False. We know this is also false. So we're not gonna enter here. But what this mean? Like why we did even this? Because we need to know, because this is binary tree, and we are looking for some node. Now we don't want to waste, or like we don't want to waste time and look for everything. We just want to know from the value which side we're gonna search. So if you give me 7 and 9, why I'm gonna look here? I know it will never be here. How did I know that? Because I know that a binary search tree, the left node is always less than the root, and the right node is always gonna be greater than the parent. So if we split this like this, notice that all the nodes are less than 6, and on the right side all the nodes are greater than 6. So immediately when this value is false, we say okay, they are not here. Okay, so it's 100% somewhere here. Now we're gonna go to this condition, and we're gonna say if this value 7 is greater than the root value, which is 6, and the q value, which is, we said 9, is greater than 6, right? Now 7 is greater than 6, true, yes. And 9 is greater than 6, yes, true. Okay, what's gonna happen if this both true? It's gonna give us true, so it's gonna enter here. So it's gonna enter the here. What's gonna happen? The root's gonna change. The root's gonna change. It's gonna return root. So this is a problem. I think this should be, oh, okay, so this is, should be, so we don't want to return root. No, we need to stay looping. So maybe else return root. So because we return root, we're gonna come back to it later. It's gonna make more sense. Now if I explain, I think I'm gonna just lose you. So we said because this 1, 7 and is greater than 6 and 9 greater than 6, we understand that it's definitely exists here, this both node. Now if DR exists here, that means between these two nodes there is couple node here. We don't know how many, right? But we are sure. But how did we know that? How did we know that these two are there's between node? Because if they are not split, right? If they are not split from 6, they're definitely there is they are like, if 7 is not less than 6 and 9 is, or how to say this, if these both value are greater than the root, that means they are in the right side, right? If they are in the right side, that means they are not split. That means the P is not the left and not in the left side, and Q is not the right side, and that means there's something between them. So in our case, it is like this. It is like this, somewhere here. They exist somewhere here. How we know this? Because they are both are greater than the root. If they are split, that means one of them gonna be less than the root, and one of them gonna greater than the root. Okay, let's keep going. So we said this give true, so we change the root, right? We change the root to the root right. What is the root right of 6? Is 8. So the root now is 8. Is 8. And then it's gonna do else. Okay, so because it's enter here, it's not gonna enter here. Now we're gonna loop. Now we're gonna loop, but this time when we loop, the root is 8. Right? And we're gonna do this. We're gonna check if 7 is less than 8, it's gonna say true. And if 9 is less than 8, it's gonna be false, which means we're not gonna enter this one, right? Now it's gonna come to this second one. Second one is gonna be if p var, which is 7, if 7 is greater than 8, it's gonna be false. And if 9 is greater than 8, it's gonna be true. Both true and false is gonna be false, which it's not gonna enter this one. Now notice here, if both of them are false, what that mean? We have split, right? Notice the split here. They are split. This one is right left side, this is the right side, so this is a common ancestor. So then if this is not true, this is not true, then else return the root, which is 8. So this is the algorithm to solve this. I'm sure there is many ways to do it, but this is probably the most common way you're probably gonna find. How to do this is just take advantage of this split. Now I might did go fast on some parts, please. I can repeat, I can explain the parts that you may get confused. Just let me know. Open mic and ask or write in chat. So who did not understand it? It's kinda hard to understand, but I hope the code did make sense. Okay, so everyone understand it? Come on, there must be someone is confused. Just type question in the chat, like, oh, what you're confused about. Can you explain 5 and error 8? Error 8, 5a, 5. What do you mean by 5-a? Error 8. Oh, the error 8. Okay. You mean like how did it become error 8, right? Okay, let's go. This will still work if 7 has its own sub root, right? Okay, let's see the error 8 question. Can you explain the error 8? How did the root become error 8? Is that what you're asking for, Karis? Karis? Yes, okay, so let's do it again. Let's make it more clean this time. So this is a root, right? We start with 6 and we have p. What the heck? Get out of me. And this is p, we said 7, and this is q, we said 9, right? Now while the root is have value, right? So we're gonna keep looping. Now we did this equation. Basically we're gonna check this. If none of them, we're gonna return this. Now p val, so p is this one, 7 less than the root val, 6, and q val, which is 9 less than the root val, which is 6. If this is true, what you're gonna do is the root gonna become root left. The value of the root is gonna become root left, and if the root is 6, the root left is 2, right? And root right is 8, so the root's gonna become 2 in this case. But if it's not right, then it's gonna go to this one, which is this right here, which is p val, which is 7 greater than the root val 6, and 9 greater than the 6. If this is true, it's gonna enter, it's gonna become root's gonna become 8, right? If none of them are true, that means this value are not they are not both of them are in the right side, they are not both of them in the left side. What that mean? That means they are split. That means one of the value is in the left side, one of the value in the right side. So automatically we understand, okay, if one of them in the left side and one of them right side, so this is the one who is the common lowest ancestor. So here, if none of this is true, we're gonna return the root. return the root, right? Which in this case gonna be 6. If this what was the root we are, but because we choose 7 or 9, we keep going, right? So which one is gonna enter if we have 7, 9? Let's see. 7 is less than 6. False or true? False. So if this is false, there is no need to treat this, right? Because it's not gonna enter this. Now let's say this one is 7 greater than 6. True. Now we're gonna check end. Is 9 greater than 6? True. So if this true and true, what's gonna happen? The root gonna change. It's become 8. So this is the part you were confused about, Karis, right? The change that happened here. Is it clear? Like how did it change? It changed because this one is true. With this, what this one it means that 7 and 9, both of them are greater than 6. So I need to get to the 8 node, not to the right. That's why we did the right 8, because root right. Root's gonna become like root right, which is the right of this, which is 8. Is it clear now, guys? Is it possible to be given a value that is not in the tree? Maybe. Maybe, I'm not sure. We can try it. Let's see. Maybe they give us something like that or not. No, they didn't give us. So how is that gonna be? How we can do a value that's not in tree? Let's do. Let's remove maybe this 3 and 5. Yeah, let's remove 3 and 5. Let's say they are not here. And we're gonna do 3, 3, 5. Let's see what the logic gonna give us. Oh wait, I think that will not make sense because I don't think they're gonna give us. Oh, will exist. Yeah. So the constraint of this is P and Q will exist in binaries. So the value is gonna be always there, exist. And the P and Q are different, and all nodes are unique. Okay, so that's condition we don't need to worry about. Second condition needs to be LF, but they will never enter, right? If it's enter here, it will never enter here again, right? If this is true, this means this is false. If this is false, this means this is true, right? Or I'm confused.
Yes, you are right, but I think that it's better to put an if condition there, because since that it will not enter there, but they will make the check, and then it can decrease the runtime.
Oh, smart. Yes. So if I did LF, then the this not gonna be processed. Okay, that's really smart. Okay, let's see if this gonna work. This one was hard to understand, but okay, so run. Okay, nice. Okay, it worked. Congrats. I hope really you understand this, guys. Please, if you didn't understand this, ask right now. I will be happy to repeat. Let me post this here. Now, there is a smell of recursion right here, right? You can do this with recursion. So we don't need the while. So we can like just remove this while, and the recursion gonna be here and here. So we can send this. Okay, so return self dots this, right? Now this one we need to give it root. Now the roots we're gonna give it this one, and we're gonna pass the same P and Q. Okay, and for this too, just this gonna be right. Okay, let's see if it's gonna work. Did this work? Okay, it worked. So recursion is also shorter than the while. Okay, who have any question for this problem, or the maybe you guys did it with a different solution? Please feel free to jump and like maybe post your solution you did it. We can try to okay, if none we can jump to the second one. I hope it's more simple than the last one. What will be the base case? I don't think so. How the base case gonna be? Probably this return root, if none of them are true. Right? So this is probably our base case if none of these are true, because it like here we stop. So let's jump to the second one. And like to think about the base case, just like think about when we were like looping through each node. When we did stop, we stop when we found split, right? And when we did find split is this one else, because it wasn't this, so it definitely this. So it's returned the root. Okay, let's jump to the balance binary tree. Let's see what it is. So given a binary tree, determine if it's height balanced, if the height balanced. Now a height balance, not sure if you can see that in string. A height balance binary tree is a binary tree in which the depth of the two subtree of every node never differ by more than one. So 3, 9, 2, 20, 15, 7, this is true. Why this is true? Because the difference is not more than one, right? So we can say that, okay, this is 1, this is 1, 2. So the height here is 2, the height here is 1. Difference is not more than 1, so this is a balanced binary tree. But if this was have like another one here, then it's gonna be 3, right? So the difference between 3 and 1 is 2, so it's not gonna be balanced. Let's see if they give us another example. So right here, so they gave us false. This is definitely not a balance. Or I need to go to doctor of my eyes. So why this one is not balanced? I guess we can start from here. Is this balance? Yes. Is this balance? Yes. Is this balance? Yes, because 1 and 1 is balanced. And now is this balance? Let's see. So 1, 1, 2. Difference is not more than 1, right? 2 minus 1 is 1. So yeah, 2 is balanced. 3 is balanced. Yes, it's balanced. 1 is balanced. Let's see. 1, 2, 3. So I'm counting the longest path. And 1. So 3 and 1. 3 minus 1, 2. 2 is more than 1. So this is not balanced. Now that's why it's false. Now how we can, let's take this to our lab and see how we can like code this or like write algorithm that detects the balance. Okay, this one is end. So we have these two. Quadricobio, if you can please mute mic, you have a background noise. So,
sorry, can I ask a question, please?
Yeah, please go ahead, Pascal.
Yeah, like from what you explained so far, what I can get, just clarify me if I'm wrong. What I can get is you are looking at two different paths, the right hand side and the left hand side. So that means that the longest path at the left or the right, the difference has to be 1. If that's what you're trying to say, right? If you look at the longest path at the left hand side, if it's 2, at the right hand side, if it's 1, then it's true. Is that it?
Yeah, it should be less than 2.
From the root, like the longest path from the root, should be less than 2. Okay.
So 0 or 1.
Okay, I get it.
So like, yeah. A balanced binary tree or height balanced binary tree is such a tree whose left and right subtree heights differ by not more than 1, which means that the height difference could be -1, 0, and 1. A balanced binary tree is also known as a height balanced tree. So I think traverse left and traverse right, then subtract if difference equal to 1. If difference equal to 1, return true, if not false. Traverse the left, traverse the right, then subtract if difference equal to 1, return true, if not false. Okay, that's a good idea. So
exactly. That's what I was saying.
This is like what a top down, like a DFS. So we're gonna launch DFS on this one, and then bottom up, or like we're gonna traverse left, traverse right.
I think if they give us the root node, then we can traverse the right separately and then traverse the left separately, and then at the end we subtract.
Yeah, maybe when you're traversing the right, you're counting you're calculating the height from the root. You return it, then you do the same for the left, then you return the subtraction of both. So that if you have to compare, right? So if it's not within that range, then it's true or false, something like that.
But we still need to check each node, right? Because like, let's say, so this is not balanced, right? To make this balance, what we need to do? We need to add 1 here. And so like if we did like this, it's gonna be like what? Can we say like this is balance right now? It is balance, right? Because the right,
at that point it will be balanced,
is 2, and this is 3, and 3 minus 2 is 1, so it's balanced. But is it all balance? Is this balance? Okay, let's make it like this. Okay, now it will make sense. So is one balance, right? It's balance, right? Because here, there is 3 here, 3 here, 3 here. So we calculate the height
Yeah,
from
from
one.
Iangazi's explanation, this is actually balanced because left and right have the same height, and if you subtract it, that gives you 0. So it's still within the range.
Yeah, but is the whole tree is balanced? No, because this one is balanced, this one is balanced, but this one is not balanced. Why? Because 1, 2, 0. It needs 1 here at least to be balanced. Did you see the problem? So we definitely need to check each node in the tree to make sure that they are balanced.
Are you gonna use breadth first?
Yeah, probably recursion. Maybe we can use recursion.
That means you have to do the same thing for each node.
Yeah, so we need to launch on the right and launch on the left. So we can start like laying down foundation. So like recursion, we can just do DFS. So let's say, okay, how we can plan it first before we. So we launch DFS on this. Now we need to set up a base, right? So what's gonna be base? So base normally is when we reach to the end, our diff is gonna stop. So why it's gonna stop here? Because probably there is no node. So if the root is none, we can return 0. Like if, like what do you call the root here? Root value if like not root or
root next or root next, sorry.
If root or like we can do roots because we're gonna call it on the left and the right and it will enter here to return. If not root, then return 0. I still don't have idea. Wait. Okay, what do you think, guys? What we gonna do? Okay, we know we're gonna launch DFS, so we probably at some point we're gonna do like left equal what this one is balance, self is balance, and then root left, root right, root right.
So when it gets to the end, it's going to return false. That's 0 if not root.
If not,
well, what you wrote on the first line, if not root, return 0. So if it gets to the end, like the last node, that means it's going to return 0.
yeah.
That's like the base case there.
Yes, so if this one, so this one gonna return 0, so this one gonna return 0 to this one 0. Now this one gonna add +1 to that 0 and return it to this one. which means we have one edge here, 1. This one also gonna return 1, which means one edge, and this tree is gonna return to 2. What's supposed to return? It's supposed to return this 2. So it's gonna do the absolute difference between these two, because maybe this is the longest path, right? So we need to return to 3 to 2, the longest path. So the absolute difference between 1 and 1 is 1 plus 1, which means 2. This can return 2. And this, what's gonna return? 3. What's gonna return? It's gonna return 1, because this is 0, 0, 1. Now 2 have 2 return. The left is returning 2 and the right is returning 1. So this gonna add 1 to the bigger number, which is 2. So 2 plus 1, 3, and it's gonna return 3 to this. 3. Okay, it's already written here somewhere. So 3, and this 2 is alone in your this. So it's gonna return 1, 1. So 1 and 3. Then we're gonna do 3 minus 1 if it's less than 2. 3. If it is false, then false, which means this is not balanced, because 3 and 1 are not there's more than one difference, something like this. Okay, so I think the idea is more clear now, just how to code it. So we need something to calculate the height, because wait 1 second. If we calculate the height of this node, the height of this and the height of this, and we found that the height is not balanced, there is no need to launch DFS on this and this and this and this and this, right? So we can calculate the height first. If it's balanced, then we're gonna launch DFS on this one, on this one. Then we're gonna calculate the height of this and this. If it's not balanced, there is no need to call def, because we know, we understand before that even if this was balanced, or like height is balanced, there is still a node in the middle of the tree that is not balanced. So we are forced to do like a check for each node. But to not waste time, let's check the height first. If it's not balanced, then no need to go and check each node. So we can do recursion for the height. So if we're gonna do the height, so I don't think we can do this right here, because we need to check the height first, right? So maybe we do a helper function recursion that will help us. So def helper. So this one gonna take what? So it's gonna take like the node, for example 1. And what is the base case? Because this so because when we are going to each node, we are like launching this to check if the height is balanced. So this one is gonna return false or true. It's gonna return false, true. I guess we can return the height, and then we can check ourselves if it's false or true. Or we can return true and false. But the base is when it's gonna reach there here, right? The end. If there is no node, then return 0. So it's gonna return 0. So if not node, if this node doesn't exist, like none, then return 0, right? Now let's say this node exists, so return how we can think of this. So if this node is if it's here, it's gonna return. If it's here, it's gonna return 0. But what if it is here? Or like, what if it is here? It should return. It should launch itself again on this left and right side, right? So return self height, or like, let's call it height. Self height on the node left. Okay, let's write some here, then we see how we can do it. Self height node right. So it's gonna launch this and this. Now I need to return. So, oh god, this is me. Okay, much better. So if I return, if I launched the height on this one, it's gonna launch it on 3, it's gonna launch it on this, right? Now this again, it's gonna launch it on itself, but here when it's gonna return, I need to calculate the max of this, right? If this return 3 and this return 6, of course I need to count the 6. So I need the max. So if this left and this is right, I need to return the 1 plus max of lefts and right. One plus the max and left of right, which is either 6 or 2. Now if I did launch this height function on 1, what's gonna happen? Let's see. It's gonna check if not node exists. If there's no node, it's gonna say there's node, so it's not gonna enter here. It's gonna go to the left, which is 2. It's gonna launch the same function on the left, also on the right, and then this function that itself launch, it's gonna launch again on the left, on the right, and this is gonna launch on the left, on the right, until it's gonna keep launching itself until we reach to the base lane. Now the base lane is this, if not node, which means this 4 right here, it's gonna launch on the left, on the right, but it doesn't have left and right, which means the value here, it's gonna be none, which means if it's gonna be if not node, because the value gonna be none. So this gonna return 0 to this, and this gonna return 0 to this. Now these 4 have 2 value coming from left and right. Both of them are 0. What it's gonna do, it's gonna do 1 plus the max of 0, 0, which is 0. So the value of the return is gonna be 1. That means this 1, it's gonna return 1 to 3, right? To 3. Now, which makes sense, right? Because there's one edge here. That's what we want, right? There's one edge here. So this return 1 to here because we want edge. This is also gonna do the same. It's gonna return 1, right? So the DFS height that we launch on 3, it have left 1, right 1. Now this gonna return to 2 something. It's gonna return the max of 1 plus 1, max 1 1, which is like 1 1 plus 1 right here. It's gonna, which means it is 2, right? Because the max of 1 1 is 1 and plus 1 is 2. So this gonna receive 2 from the left side. From the left it's gonna receive 2, and from right it's gonna receive 1, right? So this 2, it's gonna return to 1, the 1 plus the max of 2 and 1. Right? Max of 2 of 1 is 2. So 1 plus 2 is 3. So this gonna return to 1, 3, which mean there is 3 edge here. The longest edge is 3, which is that's what we want. What about 2? 2 is gonna return 1, right? Because it have 1 edge. Now 3, 1, 1 is gonna return 3 plus 1. 3 plus 1, max of them. What is that? Is 4. 3 plus 1. So it's gonna return 4. So this one gonna return 4. And then that's 4 we can like use it. Maybe. I think I lost my thoughts. Okay, now we have the height. The height is 4. Okay, let me step back. I think I lost the process of my thoughts. Okay, how do I step? Okay, so what was the goal from the height? The height was a way to see if the tree is balanced. Okay, okay, I'm back. So if the tree is balanced, now the 1 have 3 and 1. So now that because this is just a helper, so we're gonna use it in different parts of the code. Now the different parts of code will also in the root. So that return is gonna be 3 and 1. So the goal is to check if it is balanced. And when we see 3 and 1, we know it's not balanced because 3 minus 1 is less than 2. Wait, 3 minus 1 is 2. Yeah, so it's not less than 2. 3 minus 1 is not less than 2. So it's not balanced. So we can add here a check. But how are we gonna do that? Missing some part.
I think what you can do is you should use this your helper function you created for your left and right. That is, if for example we want to find the balance, if a root is balanced, so we'll just use this helper height function you created for the left and right. Then when we get two values, subtract them to find out if it is balanced.
Okay,
Yeah,
that's
it
a
has
good
to be
idea.
smaller or equal to 1, yeah, for it to be balanced. No greater than 1.
Okay, I did a mistake when I was explaining here. It's like I was comparing with Node, but we're gonna launch a helper for left tree and a helper for a right tree, and this gonna return 3 and this gonna return 1, and then we're gonna compare them. Compare this with this. Then we know if it is
Exactly.
so yeah, that's when I lost.
Yeah, so the value needs to be -1, 0, or 1 to be valid, yeah?
Yeah.
Unless, of course, we do some kind of
Yeah.
absolute thing.
Yeah, so it can't be 2, it can be 3 or more. So if 1 is good, so we can do like left minus right and check if it is less than 2.
Or greater than -2 as well. Just in case the left is longer. I mean, smaller than the right.
Oh, we're gonna
You
do
can
the
check the absolute value. The
Yeah.
absolute value
So we're gonna
of the difference.
so we're gonna take advantage of ABS. So
Yeah, that'll solve everything.
yeah.
Yes, absolute, yes.
Okay, so okay, so the height is working. It gives us the height of the left tree, the right tree. Now, inside this function, this is a different one. We're gonna call it. This is balance root, and I think if not root, we're gonna return 0. Okay, Yeah, because I think if this is balanced, we're still gonna launch another DFS on H1. Okay, let's remove this, or like let's do a comment until we see what we do there. Now, how we can use this helper? So we can do so if the height. Okay, let's do left height equal height or self height. Or let's just do height now, then later in code we height root left, and the right height equal height root, that's right. Now we have this value of the root height and left height, the right height and left height. Return helper left right, left minus right node. But that is not enough, because the height may be balanced here, but we still need to check each node, right? In the case that it was balanced, the height is balanced, but one of the nodes are not balanced. Let me know if you understand it. If not, I can clear that out. So now that we did left, we need to do like a check. If left height minus, what was the formula? Minus 3 minus 1. 1 gonna be the right, but we need absolute, right? So if the absolute of left and right minus right height is less than 2. Okay, now that we know it is less than 2, now we can launch another DFS on the other one to make sure they are also correct, or like they're also balanced. How we're gonna do this? We're gonna use the is balance too, because it is the same thing. If you notice, we did this, we launch the height on here we check if it's balanced. Now that we know this one is balanced 100%, let's check if this one is balanced. Now we'll check this one is balanced. Then when we know this is 100% balanced, let's go check at this again. So you notice it is like, again, it's gonna keep calling on the both child. So left.
Sorry.
Yes, can you repeat? I didn't hear you.
Sorry, I wanted to say something.
Yes, please.
Okay, but I really don't think we need to call that left balanced again, since we have already done it at the top here, where we have left height
This
equals to height root.
Okay.
No.
This one.
This place. So after
this one.
Yeah. Since we have done it here, it has already set the height for us. So there's no need of checking if left is balanced. All we need to do is to return true or false if the number is if it is greater than, if it's less than 2. I think that is what we need to do.
I do agree with you, but there is a edge case. So for example, this one, we can clearly count the height. 1, 2, 1. We're gonna do 3 minus 1 less than 2. It's gonna give us false, right? Right? So this is not balanced. Right? You with me, Morba? Because 2 is not less than 2. So why we need to go and do in H1? We can easily do this. Just calculate this one. It's gonna give us false, return false. That's balanced. Now there is an edge case. Let's see it. This one, 2. Now, if we did like this, what it's gonna return? Let's see. It's gonna calculate the height. 3, 3, 3. It's return 3. Okay, 3 minus 3. Is it less than 2? Yes, true. So this is balance, right? It works.
Not necessarily.
Yeah. But can you explain that, Ningas?
Isn't the calculation done recursively at each level to ensure that it is balanced?
So, like, if we see this graph, you may see it and think it's balanced, right? But the balance is like all the tree or like all the node inside the tree should be balanced.
Yes, so I'm asking if it recursively checks at each level of the node that the heights, how to say?
Yeah, then the height is balanced. So like we can't just check this side and this side. We need to check also the other. But let me expose the edge case is like, okay, is this one is balanced? Yes, it's balanced, right? It doesn't have not. It's also balanced. Is this one is balanced? Let's see. It have 1 here and 0 here, and 0 minus 1 is less than 2. Yes, so it is balanced. So okay, balance, balance. Now this one, the edge case. Let's see. This one, it have 2 here, 2 in the right side. How many in the left side? 0. Right?
So is this a binary tree?
Yeah, binary tree. So it have 0 here.
That's why it has to be balanced. Okay.
So it have 0 here and 2 here, right? Notice if we apply the formula, 0 minus 2. So we have absolute. So we are saying 2 is less than 2. Is this true or false? This is false. Right? So this node is not balanced. Right? So this one is balanced, this one is balanced, this one is balanced, 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 but this one is not, because in the right it have 2 edge, but here there is difference, it have 0 edge. So it need at least 1 here to be balanced. So the difference is 1 between the 2. So we are kind of forced to go traverse all the nodes one by one. But we got ideas like, okay, why not check the height of the first one if it was balanced or not? Because if it wasn't balanced, there's no need to jump and go travel on S1, because this one is already not balanced, right? So there is no need to waste time and launch another function for each node, right? So it's like optimization thing. We were like, okay, let's check the height. Let's check the height of this one. It's balanced. Okay, it's balanced. Okay, now that I am sure that this level is balanced, I'm gonna jump to the second level. Okay, let's launch the height on this one. Okay, check, it's balanced. Okay, now that I'm sure this one is balanced, let's jump to the second level, next level. And they keep going, right? And the moment I find someone not balanced, then I come back. I come back with like, we can do like -1. So if we find -1, we know it's not balanced. Okay, let's see. Or like we can use true and false.
Hello?
Hello? Yes. Let's go ahead, please.
Yeah, I understand what you're saying. What if when recursively going through the heights, instead of comparing and getting the highest one, we check it at that point, see if that particular node is balanced.
Okay.
So it's like if a particular node is returning 3 and then the left side is returning 1, instead of getting the highest one of 3, we can then compare at that point to see if that node is balanced, and then if it's not balanced, we return false at that point.
Yes. Yeah, that's what we're doing. So we check the height of this, check the height of this, then we decide if we're gonna go launch another one on here, another one on here. If it is balanced, we're gonna do that. We're gonna check this and this. If it's not, then we just gonna return false, or like return -1 or 0, like wherever was the result that say it's not balanced. In this case, what is it? false. So we need to return false. Okay. There's okay, let's go to clean. So we stops right here. So we know why we need the height to check h1. Okay, that's clear, but not the height. Height is not enough. We need also, when we check the height is less than 2, then launch another check with is balance on each node of the left or the right. So is balance root, that's right. So I guess everyone understand now why we have to double check again launch is balance on other part of the tree, because one of them in the middle hiding can have not balance, and we need to detect that. And now when we gonna launch this,
yes, I was thinking then at the level where you are making your condition, if apps of left
yes,
height minus right height is less than 2, why not checking if it is yes, if it is greater than 2 or
yes.
greater or equal than 2, that means that the node is not balanced. Then you return false at that level. Then then you put an else condition, and inside that else condition, then you will return is balanced left node and is balanced right node. You understand what I mean?
But isn't that long a bit? Because right here we can just do like a return left and right. Left and right, because if this balance, wait, is it left and right? Yeah, we can just do this left and right, because this is gonna return what? False. I'm still confused about this.
Zana did check for to know whether the tree is balanced or not. I thought after that if apps line, then what you have down is just return false.
Wait, which one can return false?
Like after the last conditional statement, I thought the next thing would just be to return false.
This one. This one?
After right is equal to is balanced.
Right is equal. Right is equal.
The second to the last line down.
This one. This one?
Yes. Yeah, so that the last return statement would be directly under the if.
So I need to move this somewhere?
Yeah, outside.
Like right here.
Yes, and then you just have return true. That would be at the end, at the absolute end.
Like return true here?
No. Like instead of return left and right, we'll just have return true.
Here, true.
Yes, like that. So that in the first if statement, if not root, return 0. That's like your base case. And then after your base case, you have the recursive case. That's where you're calling. So if it's after left is equal to is balanced, it's going to keep on doing that like recursively. The same for right, and at the end, it's going to return true that the tree is balanced.
So, but I'm confused. Why both? Because one of them should return false. This one should return false. Because what that means? That means this is not balanced. Because if it was balanced, it's gonna enter the F. Right? If it didn't enter the F, which means it's return false. If it's entered the F, then it should return true. and same time launch DFS.
Okay.
Is this clear? I'm still confused, but that's what it makes sense for me.
Me too. I'm also confused at this level.
Okay, let's
I was
try
thinking
to
that
repeat
you
it.
have to check if the absolute value is bigger or equal than 2.
No,
In
no,
that
no,
case,
not
it means
equal.
that the
Not equal.
I mean greater or equal than 2.
Greater?
Then
No, no, no,
in
no,
that
no, not
case,
equal at all. Not because the only value should be either 0 or 1.
or 1.
So
That's the
it
case where
should
the
be,
node is balanced.
yeah, so it's gonna be
Yes, but
always,
I'm thinking about
yes,
I'm
go ahead.
thinking about the case where the node is not balanced.
So
In the
if it's
case where
not
the node
balanced,
is
it's
not
gonna be the
balanced,
value, it's gonna be the value
yes.
like 2. So 2 and less than 2 is false, because 2 it
Exactly.
doesn't. So if it was 2, this gonna be false. So it's not gonna enter here, we're gonna return false.
Absolutely. But at this level, when you return true there, why do you have to calculate the left and the right to return the true?
No, I'm not calculating the left. I'm launching another DFS because so what? Let me write here. So let's say I launch it in here, right? I launch the balance check on here. So what it's gonna do is it's gonna come here. It's gonna check the height first, right? Now why I'm gonna check the height? Because if the height is not balanced, there is no need to check on each node if it is balanced, right? So
Exactly, absolutely.
this part is clear. That's why we need to check the height. Now we have the value of height. It got it here, save. Now we know the formula is left minus right. The absolute of left and right should be less than 2 if it is balanced. If it is balanced. Now if it's enter here, that means this tree is balanced. Okay, now that we are sure this one is balanced, we do a check mark right here and we jump to the left and right. We start scanning from this side. Now this where we're gonna start scanning. This 2, it's gonna launch another balance on this, another balance on this. And they're gonna do the same work because this is a recursion. So this left also gonna check the height of this, and then this gonna check the height of this, and it's gonna launch another recursion here, check the height, launch another recursion, and then they're gonna start returning value, right? So the one that failed this check, that means it didn't enter this loop or this if. It means it's not balanced, so it needs to return false, right?
Exactly.
And the one that entered this loop, that entered this if, it's also it launches DFS, but it's also gonna return something. Now if we did true, I think this is wrong. It should not be
that's
true.
what I was saying.
It should be the left and right. Why? Because maybe this one is balanced, but this one maybe is not balanced. So this one maybe return true, but this one return false. Right?
Exactly.
So if this is return false, we need the end of both. So this should be end. So end left and right. So what that mean? That mean is the 2. It's gonna if 2 return true, it means this one is balanced and this one is balanced. If one of them is not balanced, that means this one should return false. And yeah. Okay, that's kinda make more sense. I think we are not missing anything. We can try the code. Please jump to the mic or ask in chat. We are also confused like you, so don't be scared. Like this problem is, they say it's easy, but it's not easy, or maybe I am not good at explaining, so I made it look hard, but I try to understand it. this is what I got so far. Let's see if it's gonna work. What you think? I'm still confused about one thing. This right here. I don't know this if it should be 0 or it should be false. I think it should be false.
I think you need to do that check.
Or true.
I'm not sure that you need to do that check, since that you are checking it inside the height function.
Because
You
we
are
need the
checking if
base.
the note is
We need the base.
the base. Is it the base? Is that the base?
Yeah. Oh, okay, yeah, good. You got my idea. Okay, so if this is the base, when the check gonna stop? It's gonna stop at the end node, right? So the
Exactly.
node, if the node doesn't have 0, 0, it should return true, right?
Exactly.
Because it's balanced. So this should be true. True. Which means that 4 is balanced and 4 is balanced. So this gonna return true to this, and this return true to this. Not 0, because 0 is gonna count like false. Okay, let's take this salad to the LeetCode and see what's gonna happen. Okay, so we're gonna take this one here. This is just a helper. Okay, so this one gonna be here. So this is height outside, so we need to do add self, right? But if we put it inside, probably don't need self. Put it like this, and then, but it's not readable, right? So we do it outside, and just stop being lazy and write self. What other height we have? Okay. Pam.
You also need to call self on its balance.
Oh yes, true.
Your false. Capital F.
Yeah, true. Okay. Will it do one more time loop or like small simulation? See if this code makes sense or not. Okay, let's take this to this. You just see if it's gonna make sense. So we're gonna start from here, right? We're gonna check, we're gonna launch it on the 1. We're gonna check if the not root, of course the root exists, so it's gonna skip this. And now that we skip this, we're gonna check the left height and the right height, because we want to make sure first that the height is balanced. If it is not, there's no need to go through this calculation. Now the line height, is gonna launch self height of this one on the left side and this one on the right side. So 2 functions running in the same time. It's gonna be recursion, so it's gonna do again left. So when we're gonna call the height on this, it's gonna say if not node, of course there's node, so it's gonna skip this part. It's gonna go to the left, which mean it's this left right here, so it's gonna call another height on this one. It's gonna go another one to the right. It's gonna call another height on this one, self height node right. So the node is 2 left right, and then it's gonna wait to return 1 plus max left of the right, so the value of this. But because this is recursion, when we call left and right here, this also gonna call left and right, and this also gonna call left and right, and they are all waiting for the return, or like waiting for recursion to stop in the baseline, which gonna stop in here. And we're gonna stop because there is no node, So this can return 0, 0, 0, 0, 0, 0, 0, 0. So all this node got 0. Now they themselves can return something to the parent, right? To the parent. Now what they're gonna return is this. They're gonna return the 0 that they got plus 1. So this gonna return 1, this gonna return 1, this gonna return 1, this gonna return 1. Now this one itself gonna return something which it's gonna return again the max between left and right plus 1, which mean the one, so it should get 1 from here. This to return 1, right? No, sorry, it's return 2, because 1 and 1 max is 1 plus 1, which is 2, and this one is 1. So this one return 2, this one return 1, and this 2 is gonna return also to the parents. It's gonna return the max between 1 and 2 plus 1. So 2 plus 1, 3. And this one is 1. So now we have 3 and 1. This value, where it is stored? It's stored here, right? Because this is the original where we launched the hide. So this left have 3, this right have 1. Okay, now we're gonna do the formula. That's our recursion finish. We're gonna do the formula, which is left minus right, which is 3 minus 1, the absolute of them. So this is like 3, 2. It's gonna be 2 less than 2, which is false. So basically we're not gonna enter this loop right here, and we're gonna return false, which means this is not balanced, and that is the correct output. Now in case it was balanced, it's gonna enter here, right? Then we're gonna do the same thing we did, but this time not in this level. We're gonna jump, we're gonna call is balance on this, is balance on this right here, and then we're gonna clear this level, then we're gonna jump to this level, and we're gonna keep going until we're gonna return either false or true. Let's see the code if it's gonna work or we are just dreaming here. So what's the problem here? Left, height, syntax, invalid syntax.
There is a dot before the parenthesis.
Yeah, remove the dots.
Oh.
After height.
Create in my language. Okay. What else? Height. Root left. 2 were given. Oh, self here. So run. Node. Typo. Run. Come on, man. What's happening? Oh, its balance is B uppercase. Okay, please don't tell me there's another error. Okay, yes. Nice work, submit. Nice work. This one was very tricky one. But the performance is very low.
It's very interesting. It's very interesting, really.
Yeah. Probably there is a better way to do this. Okay, we can see some solution. Python. Okay. Is balance return root return 0. He check the height of the left, so this is kind of the same. We check the height, and if the absolute is greater than 1, okay, this is itself need another hour to understand. Okay. Okay, no problem. do we jump to the last LeetCode? Or someone have question about this? I did one before this one with a different solution, and I think it's had more. Which one? I think one of them had more better resolution. I forgot which one. Probably this one. Probably this one. No, not this one. Maybe this one. I forget which one. But I did do some solution, and it had more success. Okay, let's jump to this linked list. LeetCode. I think this one is simple, and someone needs to do this because I don't have energy anymore. Okay, so let's read it. Given a head, the head of linked list determine if the linked list has a cycle in it. There is a cycle in linked list if there is some node in the list that can be reached again by continuously following the next pointer. Internally, pause is used to denote the index of the node that tail next pointer is connected to. Note that pause is not passed as a parameter. Return true if it has a cycle in the linked list, otherwise return false. I think someone said it's slow fast pointer. I think will be great solution. Okay, let's see. Let's take it to the lab and see how we can do this. So basically, they are giving us a linked list, and they're saying, "Hey, check if this linked list have a cycle on it or not." Someone said slow fast pointer. That's probably the easy one. We did in Alex this too. So let's see how we can do that. Let's take this. So let's jump straight to it, or like let's copy this image better. So how we can do fast pointer? So we have one pointer here fast, and we have another pointer slow, right? And then we loop. This gonna go with 1, 2. This gonna go with 1. This gonna go with 1, 2. And if they catch each other, it means there is a cycle. And yeah, so this is the idea. And at some point they're gonna catch each other. I think this algorithm is called Floyd or something like that. So how we can do this? How we can code it? So slow, gonna give it the head, and fast we're gonna give it the head, right? And then while we need some condition in the while. While the fast didn't reach the end of the node, right? Because this gonna be none. If it doesn't have cycle, it's gonna be none. So while fast, what we're gonna do while fast? We need to increment, right? So slow we need to increment slow by 1 and increment fast by 2, right?
Correct.
So slow gonna be what? Slow dot next, right? Or slow dot next.
Slow to next. Yeah.
And fast gonna be fast dot next because it's gonna jump twice.
Absolutely.
And what now? we check if slow
Condition.
equal
Check
fast.
equality.
Return true. Okay, that means there's a cycle. If the loop finish and return false, which means there's no cycle.
Yeah, that's sweet.
So that's all.
Okay.
Are you not also gonna put a condition on the slow note in the while loop?
Slow right here.
Yeah. Why
Because
fast and slow?
because the fast gonna be always the first one, so it is the one that's gonna reach the none first,
The
right?
next. Mm.
While fast.
Okay.
While fast. But the problem is, what if fast reach the end? So like, what if fast, let's say this is the node, right? So fast is going like this, 2, but when we're gonna increment it, we're gonna increment it by none. So it's gonna be like none. So right here we need to add another condition, is like end fast next. Wait, fast next? What's fast next? How do we catch fast next? Because
Hello?
fast next fast next or something.
Hello? Sorry.
Fast next is
Hello?
enough.
Yes.
I have a confusion. I thought a cyclic linked list is the last one does not point to null, instead it points to another node in the list.
Like the last one.
Yes.
If it's point to the another one, it's gonna be cycle list, right?
Yeah. Is that not what we're checking for?
Oh yes. So
The cycle can exist anywhere in the linked list. It doesn't have to be the last one. It can be any one of those nodes.
Okay.
it can be between
What if it's the
this.
last one?
It can be between this one. But like we are like so the linked list, if it doesn't have cycle, it's gonna have at some point none, right? The edge of it's gonna have none. So we wanna this loop stop if we reach there. Right? So I know we need a condition here, but I just don't see it yet. Fast
I
next.
say you need to check if fast.next and then slow. I think those are the two conditions that you have to check.
And slow. But like the slow is gonna always be behind fast, so we don't need to check it, right?
Absolutely.
So if this is but why fast next? Someone explain that to me.
Since you are incrementing fast with fast.next, if fast.next does not have a next node, then that will raise an error.
If you're on the third one like that, so from the head, fast next or next. If you're on the
I think
like that. So next.
Oh, okay. So because we're gonna increment it here, right?
Exactly. You
Yeah.
can't, a null cannot move to a pointer.
So if this is none, we can't find none of next, right? If this already none, we can do none dot next. It's gonna be an error. So before we enter the loop, we need to make sure that fast next is valid node, which mean that it have some node after it, or if it doesn't have, that mean okay, there's none. That mean there's no need to do this. Let's return false because this is not cycle, because we found an edge. Okay, let's see.
Yeah, let's test it.
Let's do first without this. Run. Okay, that's the error, right? non-type object has no attribute next, because this one is none. So let's add that condition. Oh, submit. Oh, let's go. Clap for you guys.
Very, very sweet, man.
Amazing, amazing. Nice work, guys. Congratulations, because we finish the week number 5. Now we have one more week. We have like more 6 weeks. So the next week is 6, and we're gonna see this beautiful LeetCode. So next Tuesday, gonna set this tree. Wednesday we're gonna do this tree, and Saturday and Sunday we're gonna keep going until the week 7. We're gonna start checking some hard LeetCode until the last week, where we're probably gonna spend the whole week just trying to solve this one. But it's gonna be fine. It's gonna be fine. Okay, guys, if some of these parts of this PLD like is hard, just maybe go back to the recording and check the episode we did before, because this is all related to each other. So if you don't understand something, it's gonna be hard to catch up. Okay, clap for you guys. Thank you for being here. Shaza, you wanna say something? It was a while we didn't hear your voice.
Thank you, guys. Yeah, it's been long, really.
Yeah, she's busy, and she's out of love. I'm not sure if he did come back or not. Shaza, say something. Everyone miss you. I think she's not here, maybe.
Yeah,
my mic is back. Okay, it's okay. You guys have any question or something? I guess none. So guys, have a beautiful night. Thank you for being here, and let's keep growing together and learn together. Have a good night.
There's a question in the comments.
Okay, let me read it. Sorry. Which one? This one? Where's the question? I have a question. Can't we just use slow for slow loop? Oh, so like just slow? If we use just slow, that means the fast gonna be faster, right? So if our loop is depending on this, then this might how to say exceed the loop, right? So if we have like this, and we have this right here, it's too slow. Let's add one more here. So if this move 1 and this move twice, this move twice, right? And this again move once, and this move twice. Notice this one is out. You notice that? So the loop needs to stop here. But this is still true. So the loop, if it loop depend on only slow, the loop is still gonna running, but this is outside of range. So we need the loop to stop and return false. That's why we use fast, because it's always forward or step ahead. Okay, that was all. Have a good night. I hope it was clear. Have a good night. Bye.